Lesson: Recurrent Neural Networks for Sequential Data Analysis. Recurrent neural networks represent a pivotal innovation in the realm of neural networks and deep learning, particularly for analyzing sequential data. Unlike traditional feedforward neural networks, RNNs possess a unique architecture that allows them to inherently retain information about previous inputs in the sequence, making them exceptionally suitable for tasks involving time series data, natural language processing, and more. This lesson delves deep into the mechanics of RNNs, providing actionable insights, practical tools, and step-by-step applications for professionals aiming to leverage this technology effectively in real-world scenarios. RNNs are designed to recognize patterns in sequences of data by maintaining a memory of previous computations, which is achieved through loops within their architecture. This capability is crucial for tasks where the order of data points significantly impacts the outcome, such as predicting stock prices, translating languages, or even generating music. The power of RNNs lies in their ability to process sequences of variable length, unlike traditional neural networks that require fixed-size input. In practical applications, one of the most popular frameworks for implementing RNNs is TensorFlow, an open-source library developed by Google. TensorFlow provides a high-level API known as Keras, which simplifies the process of building and training RNNs. For instance, to create a simple RNN for a time series prediction task, practitioners can utilize Keras' sequential model to stack layers of RNN cells, such as simple RNN, LSTM, or GRU. These cells address the vanishing gradient problem, a common challenge in training traditional RNNs, by introducing mechanisms that regulate information flow and retain long-term dependencies. A step-by-step approach to implementing an RNN begins with data preprocessing. Sequential data must be transformed into a suitable format, typically by normalizing and reshaping it into three-dimensional arrays that RNNs expect: samples, time steps, features. For example, in a stock price prediction task, a sliding window approach can be used to create overlapping sequences from historical price data, where each sequence serves as input to the RNN. This method allows the model to learn patterns in the data that can be used for future predictions. Once the data is prepared, the next step involves defining the RNN architecture. Keras makes this straightforward. By using the sequential model, practitioners can add layers to their network, starting with an RNN cell such as LSTM, which is particularly effective due to its ability to remember information over long sequences. For example, the following code snippet demonstrates how to define an LSTM-based RNN in Keras. Python from keras.models import sequential from keras.layers import LSTM dense. Model equals sequential model.add model.compile. Pause. This model consists of two LSTM layers, where the first layer returns sequences to allow stacking, followed by a dense layer that outputs the final prediction. The network is then compiled with an optimizer and loss function suitable for regression tasks, such as mean squared error, to measure the discrepancy between predicted and actual values. Training the RNN involves feeding the pre-processed sequences into the model and iteratively updating the model weights through backpropagation through time, an extension of traditional backpropagation tailored for RNNs. This process is computationally intensive, and leveraging hardware accelerators like GPUs can significantly speed up training times. Upon successful training, the RNN can be evaluated on a test dataset to assess its performance. Metrics such as root mean squared error or mean absolute error provide insights into the model's predictive accuracy. Fine-tuning the model may involve adjusting hyperparameters, such as the number of LSTM units or learning rate, to optimize performance. Real-world applications of RNNs are vast and diverse. In natural language processing, RNNs have been employed for tasks like sentiment analysis, where the goal is to determine the sentiment of a given text. By processing word sequences, RNNs can capture contextual dependencies and provide meaningful sentiment scores. Similarly, in language translation, RNNs are used in sequence-to-sequence models to translate sentences from one language to another, maintaining the grammatical and contextual integrity of the text. The effectiveness of RNNs in these applications is well documented. For instance, Google Translate's neural machine translation system, which utilizes RNNs, has demonstrated significant improvements in translation quality compared to previous models. Additionally, in the field of music generation, RNNs are used to compose melodies by learning patterns in musical sequences, showcasing their versatility in creative domains. Despite their strengths, RNNs are not without limitations. The complexity of training deep RNNs can lead to issues such as overfitting, where the model performs well on training data but poorly on unseen data. Techniques like dropout regularization, where random neurons are ignored during training, can mitigate overfitting by preventing the model from becoming too reliant on specific neurons. Another challenge is the computational demand of RNNs, particularly for long sequences. While LSTMs and GRUs address the vanishing gradient problem, they can still be resource-intensive. Advances in model optimization, such as using more efficient architectures or pruning redundant neurons, are active areas of research aimed at reducing the computational footprint of RNNs. In conclusion, recurrent neural networks are indispensable tools for sequential data analysis, offering powerful mechanisms to capture temporal dependencies in data. By leveraging frameworks like TensorFlow and Keras, professionals can implement RNNs to tackle a wide array of real-world challenges, from financial forecasting to language translation and beyond. The key to success lies in understanding the intricacies of RNN architectures, employing robust pre-processing techniques, and continuously refining models through experimentation and optimization. With these skills, practitioners can harness the full potential of RNNs to drive innovation and solve complex problems across various domains.